Yes, I'll be talking about the integrated last mile transportation problem. This is joint work with my advisor for my PhD, John Hooker, one of his PhD students, Thiago Serra, who's now joined Mitsubishi Electric Research Laboratory. So it's joint work also with Arvind Raghunathan, which is here, and one of his colleagues, Shingo Kobori. And so this talk, or this area that we're working in, is part of multimodal transportation scheduling. The shared mobility world is growing, and it's changing the way that we're going to live, of course. You can look at all these studies that have really staggering results. I mean, $54 billion industry in 2016, expected to grow by 15% every year over the next 15 years. So there's a lot of work here. There's wide interest from lots of stakeholders, policymakers, researchers, and the like. And so what we are looking at in this particular paper is how do you optimize a particular scheduling component of a multimodal scheduling system. Specifically what we want to do is we want to look at a problem like this. You have passengers that request service on a train, and then on short distance, limited capacity pods. You might think of these as autonomous vehicles or otherwise a small little van. And so the idea is that users would be home. They have a starting position. They say that they want to take the service to a building that they want to go to, for example, for work. And the system should tell the user which train to board, so that's a fixed schedule, the train, which of the little autonomous pods to board, and then so that they can get to their destination on time and join other passengers inside those little pods. So this is how it kind of looks. There's a nice little animation we have here. You have people at home. They arrive, they board, assign trains, the train keeps on going. Again, the train is fixed, the schedule. We don't have that as flexibility. What we do have flexibility on is how these little vehicles move and who boards them. So ideally, right from home already, these passengers already know which one of these pods they're going to board, so that once they get into their pods, that can go around the network, drop people off. You can have two, I mean, normally the capacity of these things are about 5, let's just say, and you want to jointly optimize the entire schedule. So that's the optimization problem that you have in front of you, and then the vehicle goes back to the terminal, can pick up new people, they might be waiting there, or just arrived, ideally, on the trains that they were assigned to. How do you model this? So this was originally, well, a derivation of a model that you can get for this particular instance of the problem is based on a paper from Wang in 2017 from SMU, which is the same university as our first speaker. And it's kind of a state variable but general integer variable model, and so it doesn't work very well on large scale, but you can adopt it to this particular application. Your objective function has, in the paper that we have at ICAPS, a single component, which is minimizing total travel time over all the users. This includes train travel, which is kind of fixed in our setting, waiting in the station, and the transit on the pods. So that's what the objective is. We do have extension of this work, where we add a component for the number of pod trips, which can be important because you don't want to have lots and lots of trips, because then you have to maintain these things more, environmental considerations and otherwise. Some of the constraints you have to satisfy are the 5 that you see here. Each pod trip can only accommodate a limited number of passengers, so you can only assign about 5 per pod trip. Passengers must arrive within a prescribed time window, so they say, I want to get to building X at 7:30 a.m. Then we actually assume that we have fixed time windows around 7:30, maybe 7:20 to 7:40. This is the time that the passengers must arrive at their destination. Passengers cannot board a pod until the pod returns to the central terminal, of course. There's a limited number of pods, which is kind of the connecting constraints between all of these. And passengers arrive to the central terminal according to fixed public transit schedules. So a key observation is that if you just adopt this model from Wang in 2017, it really does not scale. If you want to optimize this thing readily and very quickly, you can't necessarily just apply that model. Often it cannot be solved in hours. And so there is an interesting observation that we saw, though. We said, okay, so right now the assumption is that you can have 5 passengers board one of these pods, each one going to a separate destination. That's okay for this model. The question is, what if you were to limit or restrict the problem a bit and say, actually, any passengers that share a pod can only go to a common destination? So now it's really kind of a simpler thing, right? The pods basically just have, you have to assign the people to the pods, but then pods just go to the destination, and then they come back. A quick note about the destinations is that we assume that the destinations are actually an accumulation of multiple buildings around them. There's other work that has shown that you don't necessarily want this shared mobility to drop people at each individual building, because then you get a lot of inefficiency. Rather, if you kind of cluster them together and assign them to one little like bus stop, if you will, you get a lot more efficiency. So that's an assumption that we have here. So anyway, going back to this realization that we had, we tested this out and we said, okay, here's some small problems. I guess these are 600 passengers per instance. K is the number of destinations. C is the number of pods. And we said, okay, under this restrictive assumption of one destination per pod trip, what is the gap between that and the best possible solution to the multiple destination case? And so we see that there's only modest differences, right? And of course, you are definitely losing efficiency. The total travel time is definitely higher with this added restriction, but not that much. So we said, okay, let's try and solve this problem, where we restrict that the pods can only go to one destination and then back. What's kind of, let me just skip maybe to the bottom line here really quickly. One question you might ask is this actually still a hard problem, right? I mean, it is much simpler, but yeah, you can solve it. You can prove that it's NP hard from a reduction from bin packing. So we're still in the world of challenging, but it's not that challenging. And what you can do when you have this added restrictive assumption is prove the following theorem. Given an instance of this problem where all pods go to a single destination, all passengers have equal time windows, I mentioned this previously, and the trains make regular and sequential stops. There's a particular ordering property that you can assume on the solutions which will not violate optimality. Namely, if you have two passengers that share a pod, any passenger that has a requested time between those two passengers is also in that pod. Essentially, there's an ordering of them. You can order them, and you can just break up the groups like this, and an optimal solution takes this form. So that's great. It makes the problem much, much easier. And what we can do based on that restriction is that we can now develop either a heuristic or an exact method for this problem, and then see how far away it is from the optimal solution for the whole problem, and see if we can do something a little bit more exciting and advanced. So what's the algorithmic implication? You can order the passengers by their desired time of arrival. So essentially, you just have an ordering of the, ordering of the passengers, and, this thing is bonkers. Okay, anyway, ordering the passengers, and they're ordered by their times, and you can just group them in consecutive groups. In the paper that we have at ICAPS, we introduced a heuristic based on this. It's a very simple kind of greedy construction heuristic. You start with the first passenger, and you fill up a pod until either the capacity is reached, the arrival time windows are violated, or too many pods are circulating, so you don't have enough to take the passengers. You can then define kind of a local search operation, which is a break-in shift. You take the first or the last passengers on any one of the trips, you try to move them to another pod trip and see if that improves your solution. Overall, the results look something like this. So first thing we did was we took the Wong paper and we adapted it to allow groups of consecutive passengers. Then we run this heuristic as a starting solution and then feed it as an initial solution into the MIP solver, kind of like you had to do with the CP model. And you see that the local search heuristic can definitely improve the solutions. That's this UB red that shows how much the local search improves upon the initial solution. And when you feed this as an initial solution to the MIP that was proposed by Wong, you get some efficiency in the overall solution. You see that the time for the MIP is, a little bit lower when you add this heuristic, but still, even for moderately sized problems, 600 passengers, it still takes several minutes to solve these instances. Okay, so what's an extension of this work? And this is what I want to kind of quickly go into here. I know I still have plenty of time, but I want to move into what we're working on now because I think it's really exciting, and it integrates decision diagrams, of course. And so the idea is that maybe we can, now that we have this decomposition property, we can decompose the problem by destination. Each destination gets their own decision diagram, and then they're integrated with mixed integer programming. And so the idea is it's going to be a merging of techniques. It's a whole stream of work right now where decision diagrams provide your linearization. Here we have it for one for each destination. And integer programming will encode the constraints and optimizes over the collection of these. You then reformulate the problem as a consistent path problem, where you want to find a path in each one of the diagrams that coincide on the variable assignments, and then optimize whatever metric you have. Our extended objective function now incorporates number of pod trips, and so we can actually do these two objectives that I talked about in the beginning. So what is the decision diagram? It's really a state transition diagram. These things are kind of one and the same. What you end up having is, suppose this is one destination, so all the passengers that are going to building X. Every layer corresponds to a passenger, and the arcs will dictate whether or not they are the passenger in their pod trip that has the latest requested arrival time. Dashed arcs mean that they're not, so if you look at the root node here and you go to here, that means that passenger 1 will not be the last passenger, the one with the latest requested time, in the pod trip that they take. The solid arc means that they are. Trust me, details in the weeds, but you can build a diagram for every single destination where every single possible solution for that destination is encoded through paths in this diagram. What you have to do then is you have to solve the consistent path problem. You have one of these diagrams for every single destination. This is a particular example that I can just show, which has binary variables, 3 different decision diagrams. Think of each one of these as state transition diagrams for each of the destinations. You end up looking at paths in each one of them. For our problem, they encode specific solutions for every single passenger going to a destination. You can solve that individually, and then that has implication for the other diagrams, of course, because you have a limited number of pods. For this particular example, if you were to optimize just for one destination individually, you end up with a solution that is not optimal, of course, because it's only myopic for that one. Alternatively, you can try to solve the whole thing together and you get an optimal value of 21. This is for a maximization problem. And so the idea is, let's build a decision diagram or a state transition diagram for each one of the destinations, and then optimize over all of them concurrently in order to find a globally optimal solution. You can do this in various ways. One way that's been proposed is by using this longest or shortest path polytope. So you take each one of your diagrams, you associate flow variables, and you just make sure that you have a path from the root to the terminal. You know that every single destination has a single decision diagram, and every single solution for that destination is encoded by some path. And so by concurrently optimizing over this, you can optimize for your entire problem. Here's the overall solution framework. You take your instance, build a bunch of these polynomial-sized decision diagrams. Pseudo-polynomial actually depends on the width of the time windows, and that increases the number of arcs. But still, in the instances that we look at, it's a generally reasonable-sized decision diagram. And then you optimize over it concurrently using a weighted consistent path problem. Take-home message, and the details are, of course, coming out. You can read about that soon. So we can solve now this problem for up to 10,000 passengers in less than 1 minute. So this is really fast. It is real-world applicable. We use not the classical way of solving this consistent path problem, but actually a branch and price, where each path actually gets a variable, and then you have a, well, I guess you would call it even just column generation because the bound is quite good. And then you can optimize really quickly over these structures. If you were to use the MIP from Wang, I mean, 10,000, you simply cannot load it into a computer. But because each one of the diagrams are actually quite small, it's a reasonably sized problem. And again, you can solve 10,000 passengers, 50 destinations, 600 pods within a minute every single time. Here's a, here's a performance profile. Here's time in seconds. These are the number of instances solved at a 450. The blue line is kind of the standard consistent pathway of solving. The orange line is if you solve it by this branch and price procedure. Also, I mentioned that we have 2 objectives that we look at now, not only total travel time, but also the number of pod trips. And we consider just a convex combination. And you get like kind of a nice Pareto frontier, right, of course, because as you move one up, the other one gets more important. But it's nice to see that we can optimize over both of these metrics very quickly for problems with lots and lots of passengers. Future work involves a lot of things here, right? I mean, you want to think about what actually happens in a real-time deployment of something like this, where you have different arrivals coming in, and a lot of other considerations that we're working on. But this is the start, and yeah, if anyone has any questions, I'd be glad to answer them.
Thank you for a very nice talk. One of the considerations for last mile that we've previously worked on, not Wang, but another colleague of mine, is that passengers may not want to wait that long at the station for the pods. So if you are in a situation where there's not enough pods, after X number of minutes, there may be, they may renege, they may decide to leave. So have you considered that, or maybe that's an extension of the work?
We have not, but that's a good idea. I think the leaving of passengers is something very interesting, right? Because even I might leave even if the pod is kind of coming very quickly, right? Just some kind of stochastic thing happens. So it's definitely something of interest to look at, and we have not considered that yet.
Yeah. Okay.
Yeah.
So it looks like you have some sort of allocation routing problem with cool temporal constraints on your trains, because you're allocating passengers to the train, and then so those are customers allocated to the warehouse, and then you've got routing constraints on the pods coming out of the train. And so you might want to think about looking at that literature, because if you're solving these things that quickly, there might be a whole lot of other cool problems you can solve.
Yeah, and these are quite related to dial-a-ride problems too, and so yeah, we're looking at the similarities, differences, and again, there are some restrictive assumptions here that allow us to scale to 10,000, but still, right, I mean, you get a solution so quickly, you can then maybe modify it with some local search or something like that. So yeah, absolutely, we'll take a look at that. Yeah.
Thanks. I've seen a demo about a month ago from a startup based in New York showing this in accelerated time, but not with 10,000 passengers. If you want to know the company, I can give you some details offline so we can become friends almost geographically next to each other.
I do want to know that company. Yeah, very good. Thank you, yes.
And I would like to know if what they are showing is actually true. Right. So it would be good to hear back from you. But, so you chose to apply this or look into the first last mile. Would it be much different or computationally more difficult to do it for the last mile, when the passengers come with a train and they all want to get home, which would be similar then to goods delivery, either items or bulk material delivery? Is this applicable?
It is, and I believe directly applicable. Of course, depending on the assumptions that you have, it is. What we would have to kind of expand upon is if you have people going in multiple directions. I don't think then it's immediately applicable. But I do think that for the last mile, we could probably directly apply this algorithm.
Okay.
Do you think that the assumptions that you made would still apply if you had multiple train stops that were reasonable for the passengers to get off at?
No, but we did also look at how far from optimal they were for some certain variants like that, and still not that far. Now, of course, we had a really nice talk in the masterclass about instance spaces, and so I think as a community we have to be careful about saying, oh, we're this close to optimal. But for the instances that were motivated by industrial partners, we were fairly close. So yes, it's a good point and something we have to think about, yeah.
Okay, that's it then. So let's thank the speaker again.